Okay, last chapter 12 video. I got good news. I'm not going to give you any sort of arc lengths of polar curves on your exams, but I will ask you to find areas. All right. This is just for homework. You might be like, I don't want to do this. I'm not even going to do my homework. All right, do you. Hopefully you have it locked in and you know the process, but there is some pretty wonky stuff. So I'm going to save you the time of watching me do a proof. Arc length of a polar curve, let f have a continuous derivative on the interval of alpha to beta. Angles. When you see Greek, just think angles. The arc length of the polar curve, r equals f of theta, on the interval from alpha to beta is, well, it's the square root of the function squared plus its derivative squared. D theta. Okay. Cool. So we're going to run through, we're going to find the arc length of the spiral r equals theta. Those are kind of cool. I like those. So for part A, saying the radius is just equal to the angle, so it's just going to start off at 0, and it's just going to go, it's going to get really freaking big. But we're only going to go around in one freaking circle, so it's going to look, a little something like this. You know, wow, like one of those little shell-looking thingies, which I'm drawing a blank on. That represents like the Fibonacci sequence. But okay, so let's just start going. So we're going to say the length of our curve is equal to the integral from 0 to 2 pi. See? 0 to 2 pi. We're good to go. We don't have to use any sort of symmetry because there's no cosines or sines in there. And there is no symmetry with this. You're not going to be able to find it out. So we're going to take the square root of, well, our function. Remember, r is the function, is equal to theta. And its derivative is equal to 1. No, we just have theta squared plus 1 squared d theta. 0 to 2 pi integral of theta squared plus 1 d theta. Man. How the hell do we solve that? How do we do there? Huh. That might be a trigonometric substitution. That's a trig sub. Do you remember trig subs? I'm not going to get into it. But dude, final exam. Half of it's freaking integrals. I'm just jumping to it. I don't want to do the trig sub. I don't feel like doing the trig sub. Do you remember the trig subs exist? Do you remember the trig subs exist? I'm going to let you go through it. If you don't like thetas, write it as x. It ends up being half of the theta times theta squared plus 1 plus 1/2 the natural. Oh, you remember those natural logs that used to always pop up? Theta plus the square root of theta squared plus 1 from 0 to 2 pi. You remember all this stuff? You'd have to go and plug all of it in. And then, oh gosh, this would turn out to be, jeez, pi times the square root of 4 pi squared plus 1. What would the other part be? 1/2 ln of 2 pi plus 4 pi squared plus 1 minus 0, 0, 0, 0, 0. Gone. Oh, wow. Could you still solve a trig sub? Could you? Could you? I hope so. That's going to be a big piece. And again, I'm purposely not going into the steps because we've already covered that. That might be something if you're like, I don't remember trig subs. Go back. Start working on trig subs again. That's going to be on your final. There's going to be much more about your integrals than there is necessarily about polar. So go check it out, huh? Now next, we're going to want to go and find the arc length of the cardioid. And really, I'm just setting this up to show you how much stuff in integration you may have forgotten, because integration, very important. So we want to go find this, knowing that the arc length is going to be from, well, 0 to 2 pi. But oh shoot, gosh dang it. Oh, so it's going to be our function squared plus its derivative squared d theta. But there's a cosine in our problem. So if you don't know what this looks like by now, I don't think you've been watching any of the videos. I think you just jumped to this one because we keep messing with the same one over and over and over. There is our cardioid. 1 plus cosine of theta. See, when I'm looking at this and I'm giving you 1 plus cosine over and over and over and over again, I'm like, well, sweet, on a final, I just give you 1 plus sine. I can keep it just as simple. Just make it symmetric about the y-axis instead of the x-axis. But, you know, neither here nor there. All right. There we go. We want to find it. So we do not want to do this. There is a cosine in here. If you try and go from 0 to 2 pi, you will get the wrong answer. I promise you. There is symmetry. Let's go from 2 times 0 to pi. And now we can start punching that stuff in. So we're going to take our f, which is 1 plus cosine of theta. We pop it into that squared, and then we got to square up its derivative. So we're saying our function is equal to 1 plus cosine. And then its derivative is just equal to negative sine. Once we work this whole thing out, what do we get? What do we get? What do we get? 0 to pi. So this is 1 plus 2 cosines of theta plus cosine squared of theta plus sine squared of theta d theta. All I did was I expanded out the first part and the second part. And oh, wait a second. Do I see a cosine squared plus a sine squared, a cosine squared plus a sine squared? That's just 1. Meaning we have 2 times the integral from 0 to pi, the square root of 2 plus 2 cosines of theta d theta. Man, what do we do here? What do we do here? Do you have some fancy trig that you can do here? Do you see it? Do you know how to integrate this? This is too tricky. This is way too frickin' tricky, okay? This is way too tricky. Did you know that cosine squared is equal to 1 plus cosine of 2 theta over 2? You knew that, right? We're going to use some backwards logic. Once again, too frickin' tricky. I'm not going to do this with you. But we could also say this. We could cut this in half, which would cut that one in half, giving us 1 plus cosine of theta over 2, which means we could multiply this over to the other side and say 2 cosine squareds of theta over 2 is equal to 1 plus cosine of theta. Again, this is too tricky. This is too tricky. I'm not going to be this much of a dick, okay? I promise. Maybe in your homework, because everything's fair in the homework, and then we can say this is equal to 1 plus cosine of theta. You know, 1 plus cosine of theta is equal to 2 times cosine squared of theta over 2. Oh my goodness. So 2 times 2 cosine squareds of theta over 2. How's your trig? Is it pretty good? Good thing we've spent multiple semesters getting better with it. So it looks like we have 2 times 2 times 2. Oh, I forgot the square root. Come on, man. That doesn't work. So we have 2 times 0 to pi over just pi. Just pi. Just pi. And now we have 4 times cosine squared of theta over 2 d theta. But we know the square root of 4. That's 2, so we yank that out. And now we have the square root of cosine squared of theta over 2 d theta. Well, cosine of theta over 2 is always positive between 0 and pi. Do you know that? Cosine might be positive than negative, but we're cutting it in half, so we're actually only looking from 0 to pi over 2. Therefore, we can just remove the square root and the square, and we get cosine of theta over 2 d theta. Which means our antiderivative of this is going to be 8 sine of theta over 2 evaluated from 0 to pi. You pop that in, you get 8 times sine of pi over 2 minus 8 times sine of absolutely nothing over 2. That's just 0, so we get an answer of 8. There's lengths of curves. The problem with these lengths of curves, is they require some really tricky trick. Really tricky trick. So we won't do it on exams, but go through, do your homework, do your best. There's your formula. And guess what? I don't think you need to listen to me and talk anymore. Isn't that nice? You don't have to listen to this weirdo speak any longer. Hopefully we are done with this class. I don't know, maybe in future semesters I move around the timing of these things, but hopefully we are done. And go listen to another teacher babble at you. It's been fun. All right, see ya.